right? It's called quantum fluctuation. Now it's getting more talked about because of many, many different reasons. But so it's becoming more popular in people. But only a few years ago, if you talk to people about, infinite density in the vacuum, they'd look at you and go, "Oh my God, what are you talking about?" They think you're talking about a vacuum chamber in a laboratory somewhere. So I was, so how did they renormalize this? Well, they took a thing that's called a Planck's distance. And I'm not going to go into much details on how they derived this number. But it has to do with the Schrödinger's equations. And the Planck distance is 1.616 multiplied by 10 to the minus 33. This is a small little dot. And basically they say this little dot is the smallest thing the universe does. Right? We'll make the dot. See? Here's my Planck's length. And they say the universe goes to that small and then stops. It's like, I'm done. I'm out of here. This is way small enough. I ain't doing nothing smaller. Okay. And then what they did is they went and see how many of these Planck's lengths, right, would fit in a centimeter cube of space, to try to renormalize the infinite density of the vacuum, to get a closed number. So they stacked the Planck's length into a centimeter cube of space, basically, and calculated that the density of the Planck's length would have to be 10 to the 94 grams per centimeter cube. 10 with 94 zeros of these Planck's length in a centimeter cube of space. Well, now they had a finite number. But what is that finite number? Let me give you an idea. If you took all the stars we observe in the universe with the largest telescope on Earth, actually off the Earth, the Hubble, and you stuck, and we see 100 billion galaxies. Each galaxy has over 300 billion stars in it. Most of these stars larger than our solar system. Okay? And you took all that stuff with a huge trash compactor and you squashed it into a centimeter cube of space. You still would not have 10 to the 94 grams per centimeter cube of density. You'd still be short. Okay, so you guys got a finite number. It sounds pretty infinite to me. Maybe we should learn to deal with infinities instead of trying to renormalize them. Because, people got Nobel Prizes for this. So 10 to the 94 grams per centimeter cube is actually what's called the vacuum fluctuation density in quantum space. Meaning that the vacuum is not empty. It's extremely dense. But why does it feel like the vacuum then? It doesn't feel so dense either after, a night at Burning Man. with what happens there, how can the vacuum be so dense? Well, if the vacuum is everywhere and infinite in nature, then it's in perfect equilibrium. And if it's in perfect equilibrium, there's no way you're going to feel it. It can have infinite forces in it, but if it's in perfect equilibrium, you're not going to know it's there. Just like a fish inside the ocean, in the water, will never know it's in the water until you take him out of the water and it feels a different density. We have no way to feel a different vacuum. So we think of the vacuum as empty, when actually it's full. And you can come to those conclusions yourself by simply realizing that if everything is radiating in the vacuum cannot be empty. So I was, amazed, and I'm like, okay, well, let's go with this. The universe is expanding. The vacuum is contracting to infinity. And all of reality emerged from the feedback between expansion and contraction. It becomes really clear then that the expansion part would be the electromagnetic radiation part of the universe,